Good evening, everyone. Welcome to this awesome session where we'll be covering physical science and the journey of preparing you guys for your preliminary exams. So, guys, please remember your prelim exams. This is for a lot of you the first time you'll be writing a full exam for this year. So, keep in mind you're covering all the content, some of it from grade 10, some of it from grade 11, a lot of it from grade 12. So there's a lot of content to cover. Please make sure you guys pay a lot of attention in the session. Now, before we get started, 3 minutes past 6. I'm going to give everyone a chance, like 30 seconds. If you've got a friend who's in grade 12 who will benefit from this session, someone in grade 12 doing physical science right now, send them a text and say, listen, class is in session, join right now. Because once we get started, I want to kind of push right through to the end. All right. My name is Mr. Rangaka, and welcome to the session. Thank you guys for trusting the learning space for your educational journey. Someone says they can't hear anything. I'm just not sure who's my admin. I think Nell is my admin. Nell, can you hear me at all? Okay, I got a thumbs up there. Um, so I think the person who said they can't hear anything, you have to connect to audio. So what you need to do here, previously we were using webinars, now we're using an actual Zoom meeting. All right. Because one of the things we realized with our webinars is that our webinars were cutting out. There was a cap of 500 attendees. And sometimes we'd get to the limit and we couldn't have more people join, especially the math sessions. So we've moved to normal Zoom meetings and then we've done the up to 1,000 people in the session. So please just on your screen at the bottom, you should see a little headphone icon. Click that and then either join via Wi-Fi if you're using Wi-Fi or via mobile data. Then you should be able to hear. It doesn't help because you can't hear me saying this. But now please just type that in the chat if you can help from an admin perspective. If they can't hear sound, they haven't connected to audio. So they need to go and click the headphone icon at the bottom of their screen and then click join via mobile data or join via Wi-Fi. And that will allow them to be able to hear the session. They'll type that for you so that you can hear. But to just check that I've got everyone else and they can hear in that case there. What I love doing in my sessions is I love lots of interaction. So those of you who were with me when we were doing the winter school, you'll remember lots and lots of interactions, what I want. So there's multiple ways to interact. I'll give you guys a heads up and a hint in terms of how that can happen. Number one, you can use your Zoom reactions. Unfortunately, we're not live on TikTok today. For some weird reason, TikTok has been blocking our lives. And we've been appealing with them to try get us back online on TikTok. So if you have a friend who's used to joining us on TikTok, tell them that we're not live on TikTok. They should use the Zoom link for today, please. So one of the ways you can interact with us is Zoom reactions. So Zoom reactions is raising a hand, it's giving a high five, any kind of emoji. So what I want you guys to do now is just test that feature out. At the bottom of your screen, you should get an option for reactions. Just click reactions and then give me your Zoom reactions. That's one way of interacting. Another way of interacting is using the chat feature. So now a small little thing, we're not using the webinar feature. So we no longer have a Q&A and a chat. We just have a chat, right? In this format here. So post your questions in the chat, post your answers in the chat, and that's going to basically be useful. And that's the second way of interacting. The third way of interacting is if you actually want to ask a question live. Put a hand up, and then I will unmute you, and then you will be able to ask your question live. I like live questions. I think they're pretty cool because it gives you a chance to explain further. Sometimes when you guys type questions, you might not be as clear as you'd like to be, and then it requires me to ask follow-up questions. But if you can just put a hand up, I'll unmute you, and then you'll be able to speak and ask the question live. Fantastic, guys. Okay, I see the numbers are increasing, which is fantastic, right? Just remember, for those that have just joined, welcome to the session. If you've got a friend who's not in the session right now, please send them a message saying class is in session. Please go join the class right now. You can forward them the link. There's a link that's been pasted in the meeting chat. If you go to the meeting chat, you'll see the link. Just forward that message on to your friends, just so that they can join this session. All right, I'm going to get started just now. I want to get my screen share on. And as a reminder, today we are covering the Doppler effect, which we should have a little bit of fun with that topic. All right, cool. Let me get my screen share up and then we'll get started on this session shortly. Okay. Give me 2 seconds. Okay, the screen share is loading. Okay, it might need me to change cables if it doesn't come up. Okay, it's loading. Okay, I might need to change cables. Give me 2 seconds to change cables. It doesn't seem to be connecting. Okay, while I do that, just a reminder, guys. So, like I mentioned, interaction is pretty important. So use your reactions, use your chat feature, put the hands up if you want to talk or ask a question live. And then the other thing I want you guys to keep in mind is we learn best. So if I ask if you guys are with me and you're not 100% with me, then you're not with me, right? 99% is not 100%. So if I say, are you with me? You must be 100% with me. If you're not 100% with me, then at any point, just say, listen, I'm not understanding, but this is the one way I want you guys to do it. I want you guys to ask very high quality questions. So what do I mean by a high quality question? A high quality question is one where you say, sir, I understand how you did the second step where you wrote 1, 2, 3. Where I get lost is in the third step where this happens. Simply saying, please repeat, or I don't understand, are not high quality questions. It doesn't give me a sense of what you don't understand. It doesn't help me help you, essentially. So help me help you by giving me high quality questions, by specifying exactly where you were lost or exactly where I would have lost you, right? And then hopefully, if we can do that, we are sure to have a good time together. Let me try and do the screen share again. Okay. It should be coming up shortly. Technology is not on my side today. Okay. Apologies, guys, for this. My screen share is not going on. I'll try again and then see if I can make this any different. Let me stop and try one last time. I have no idea why this is doing this to me today, of all days. Let me change cables for the very last time, and then hopefully this will work. All right. Okay, this is a brand new cable in now. Share screen. Here's my iPad via cable. Share. There we go. Okay, perfect. I think it is sharing now. Please just someone give me confirmation on your side that you can see my screen. You can do this by popping something in the chat. Give me a thumbs up. Give me a Zoom emoji. Thumbs up to see that, yeah, we are connected. Thanks, Auguste. Thanks, Lerato. Thanks, Cabello. Perfect. Okay, I can see you guys there participating. Fantastic, guys. Let's get started with the Doppler effect, right? I'm going to switch my video off for the duration of the teaching part, just to save you guys some data. And then I'll put it back on and you can see this ugly face at the end of the lesson again. Right. Okay. So again, welcome to our prelim exam prep workshop series. Today we're going to be covering the Doppler effect, right? So before we go far, there's a document I want you guys to get very, very familiar with. It's a document that's freely available to download on the DBE website and probably plenty other websites as well, right? This document is called the examination guidelines. All right. So your examination guidelines, guys, if you don't mind, please try and refrain from annotating the screen because it does cause interruptions for everyone else who is watching. So please just try and refrain from annotating the screen at any point. I'll try and find an opportunity to give you guys a chance to do that. But while we're busy, please try not to annotate on the screen. Okay. So your examination guidelines is a document that takes you through what is expected of you in the exams. It tells you the breakdown by topic. It tells you the breakdown of the types of questions you'll get. And more specifically, it tells you per topic what you need to know and what you need to give back. So this is one of the great parts about the examination guidelines, right? So in all of that, I've just extracted the part that talks about the Doppler effect so that we can go through it together, right? And then make sure that we understand and are ready to give what they need from us in this particular session. So from our examination guidelines, they want us to know the following. So again, here they're talking about the Doppler effect, which is about relative motion between source and observer. This section must be read in conjunction with the CAPS page 121 to 122, where in the CAPS document it unpacks things even further into a lot more detail. But this is a nice summary of what you should know. And then basically, this tells you what you're going to get tested on. So these 6 points are what they can test you on when it comes to the Doppler effect, which shows you a lot of the times for me, I find it's nice that you can actually see that, oh, if I can understand these 6 bullet points, I can then know and do and perform well with this topic. And Doppler effect is one of those topics that's pretty chilled, right? So with sound and ultrasound, and then the last one is with light. Let's go through the 4 points. So point number one, it says, state the Doppler effect as the change in frequency or pitch of the sound detected by the listener because the source and the listener have different velocities relative to the medium of sound propagation. So that's the definition you need to be able to know and give back. When they say state the Doppler effect in words, you'll almost always get that definition, right? In your exam, memorize it, be able to give it back. Super, super important. That's point number one. Point number two, it says, explain using appropriate illustrations the change in pitch observed when a source moves towards or away from a listener, right? The illustration can be a physical illustration of drawing sound waves. The illustration can be a graph as well. There's a question today we'll do that requests us to do a graph. So very, very important. Okay. And then what I'm going to just ask my admin now, please just note questions there that do come by because we're not doing a webinar and it's more just a normal meeting. Sometimes I might miss certain questions that come by. So just remind me there. I see someone says, please raise your voice. Let me know if I am speaking too softly. I thought I'm speaking quite high. If I am speaking softly, someone else please confirm. Otherwise, I think December, maybe your volume might be a bit low, but I'll try speak at a very high, or I'll use my outside voice as well. Okay, awesome. So that's point number one. That's point number two. Point number three, solve problems using the equation FL meaning frequency of the listener, right, is equal to V plus V or plus or minus VL, where V is going to be the speed of sound in air or whatever medium of propagation it is. In the Doppler effect, we're dealing with air. Air is our medium of sound propagation. So V will be the speed of sound. The speed of sound is not like the speed of light. Yes? Okay, someone says try increasing your volume. Um, I'm not sure now if that message is to me or to Unesimo. On that side, just let me know if I need to increase my volume or they need to increase it on their end. Right. When I look at my sound levels, it seems to be pretty high. So okay, just double check. Cool. Thanks now. Okay, she says the projection is fine on her side. So the equation FL is equal to V plus or minus VL, where V is the speed of sound in air. That is unlike the speed of light, which is a constant. The speed of sound will usually be given to you, right? It's usually just over 300, sometimes 330, 340, somewhere in that range. But please look out for that amount. They will usually tell you what that amount is, okay? And then VL is the velocity of the listener. So that's the speed or the velocity with which the listener is moving. Guys, please, 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 I did make the request. Do not annotate on the screen. It is very disruptive to those that are watching, especially to me as a presenter, right? One of the key things and a tenet that we have at the learning space is respect. So if we need to respect each other, because every time you annotate, I have to pause and then it disturbs the lesson and then you're interrupting it for all the other learners that are in the class. So please, please don't annotate on the screen. Thank you very much. All right. So VL is the velocity of the listener divided by V plus or minus VS, where again, V is the speed of sound in air. And then Vs, which is the velocity of the source. So the object or the person that is listening or receiving or perceiving the sound that has been emitted, right? I mean, sorry, the source is the one that's emitting, yeah, that's emitting it. The listener is one that's perceiving and receiving it. Times Fs, which is the frequency of the source, that's the one that's emitting that particular sound. Okay, cool. Raphael, please don't annotate on the screen. It is very disruptive when you do that. All right. And then it says when either the source or the listener is moving. That's a very important part, right? When they say either the source or the listener is moving, is that it means that you're not going to get a question where you will have both of them moving. You'll either have source moving or you'll have listener moving. Meaning, whenever you do this, either VL or VS will be zero. And then one of them will have a value. So that's very important to note when you get your questions. Only it's either the source or the listener. Only one of them will be moving. The other one will be stationary in the questions you get. Awesome. Let's look at point number 4. Point number 4 says we need to be able to state the applications of the Doppler effect, right? So what's the Doppler effect used for? And there's a lot of uses for the Doppler effect. We're going to go through some notes now and have a look at it. So, you use a Doppler effect for what most drivers hate, this what we refer to as the speed trap in South Africa. In America, they call it a radar gun. But it's that device that the cops use on the side of the road to check what speed you're moving at on the road. That uses the Doppler effect. You've got um, in medical terms, when you ever see those ultrasounds of the baby and sonar uses the Doppler effect, right? There are a lot of uses of the Doppler effect at the end of the day, so you can definitely check those out. And then we'll go through some more examples as we go through. And then we need to also look at the Doppler effect of light. So with light, red shifts in the universe, and that's evidence for expanding universe. So number one, you have to be able to explain redshifts. So what are redshifts? Number two, you must be able to use the Doppler effect to explain why we can conclude that the universe is expanding. That's also very important. So those 6 steps are all the things they can ask you about. I've got about 6 questions lined up. I mean, not 6, sorry. I've got 3 question 6s lined up. Question 6 is usually your Doppler effect question. I've got 3 of them lined up for us to practice and do today. So we'll do a lot of practice together. I'll often ask you guys to do a lot of questions with me, give me answers, and then you guys can just play along as we do that. Perfect. So let's jump into some theory. Then I'm going to pause and do a little bit of a simulation. And after our simulation, we're going to jump into some questions, right? So let's start off with that definition, right? So the definition of the Doppler effect, or when they say state the Doppler effect in words, that is going to be the change in frequency detected by the listener because the sound source and the listener have different velocities relative to the medium of sound propagation, right? Very important that it's the change in frequency that's detected by the listener. Or you can even say the apparent change in frequency, right? Apparent meaning the source doesn't actually change the frequency it's emitting. It's just the person who's listening hears something different. So it's an apparent change in frequency or the frequency that's detected. It'll be different, but it doesn't mean that the source actually changes its frequency. That's very, very important, right? And then when we unpack the medium of sound propagation, what is that? So the medium of sound propagation essentially is the substance that sound waves are traveling through. Doppler effect, I said, usually air, right? It can be water, it can be other things, but usually we're dealing with air. That's how we normally hear sounds as humans. Please note that frequency determines pitch, right? So frequency is a property of waves. It's a wave property, right? It's how many full waves you see or hear per second. And pitch is a property of sound, right? So yes, those two things are related, but frequency is not pitch, but frequency determines pitch. So we can infer or we can say, oh, I know the frequency was high because the pitch was high. Because a high pitch means it was created by a high frequency. A low pitch means it was created by a low frequency. So therefore, higher frequency equals higher pitch in this case. In this case there, lower frequency equals lower pitch. Very, very important. Right? Then what I want us to look at now here is why this happens, right? So here's a little picture, and like I said, we will do a little simulation together. Here's a little picture that shows you visually why the Doppler effect is what it is. So number one, right? I want you guys to answer this question here. Let me quickly hide this before you see it. I've got listener number one on the left-hand side and listener number two on the right-hand side. There's an ambulance moving from listener number one to listener number two, right? I want you guys to tell me who will hear the higher pitch sound, listener number one or listener number two. This is your chance to now put your answers in the chat. So type now in the chat, write either one or two. Will listener one hear a higher pitch or listener two? Thanks, Karabo, for your answer there. Thanks, Onesimo. Thanks, Ryan. Thank you for all the quick answers there. Fantastic. Thank you, thank you, thank you. If you haven't put your answer, don't panic. Take your time. Whoever's annotating, Boniswa, please don't annotate the screen. It is quite distracting. Okay, thanks for all the answers coming in. You guys are awesome. Guys, please don't annotate the screen. We can see who's annotating the screen, and we will block you from the class if you continue to do that. Okay. Fantastic. Great number of answers there. And it's listener number two, right? So remember, so this ambulance here, let's say, for example, it's emitting a sound, the siren, right? And let's say that siren is playing at whatever, let's say 200 hertz, right? It's a random number. It might not be what it needs to be, but let's imagine 200 hertz. Now, as you can see what's happening, and the simulation is going to show us this quite nicely later on. It emits the sound, and then the sound waves propagate radially outwards, meaning when I say, hey, people in front of me can hear me, people behind me can hear me, people to my left can hear me, and people to my right can hear me, because the sound waves go in concentric circles away from me, right? Now, if the ambulance is emitting the sound and now moving forward, it means the ambulance is moving closer and closer to the sound waves it emits in front of it, right? At the same time, it's moving further and further away from the sound waves it's emitting behind it. Now, that has got two very important ramifications or the resultants of that. In front, as I do that, my wavelength becomes shorter because I move towards the wavefronts every time. So you'll see I've got a peak, trough, peak, trough, peak, trough, peak, trough, right? Very high frequency in this case here. But at the back, I've got peak, trough. Let me redraw this one. Peak, trough, peak, trough, peak, trough, peak, trough. This is a very low frequency because I've got a much longer wavelength, right? Wavelength we have as lambda, right? And then also here, very short wavelength. I might have drawn that lambda the wrong way around, which is the right way to draw lambda. One of those two. Apologies. My brain is a bit fried. So we can see my wavelengths are very short. Your wavelengths basically here are going to be these gaps. Let me show you here. Any space between two points in phase. So this here, will be a wavelength, right? But also here, that space there is one wavelength. So you can see at the back, I've got very long wavelengths. Long wavelengths give me a very low frequency because it's a long time in between wavelengths. But short wavelengths give me a very high frequency because it's a short time in between wavelengths. And then the high frequency is linked to the pitch. It's a high pitch, low frequency is linked to a low pitch. So you guys got the answer right. Everyone that gave the answer two. If you got the answer two, please celebrate in the chat. How we celebrate is by throwing dancing emojis, fire emojis, clapping hands emojis, laughing emojis, any emoji that you want to use to celebrate, put that in the chat right now to celebrate. Thanks, Chantal, for your quick fingers there, and everyone else. Fantastic. Okay. If you didn't get it right, but you see where you went wrong, this is another chance for you to celebrate as well. So jump in there with the celebrations. It's going to be awesome because that means we're going to be passing this topic and getting flying colors, and you guys are all going to do well for prelims. Okay. Your teachers are going to try set very hard papers for prelims, and we're not going to let them win. We're going to come very prepared because of the learning space, right? Okay. So now that we've done that, let's quickly have a look, right? So, the last thing I wanted to say here, if the ambulance is emitting 200 hertz, the listener in front will hear a higher pitch than 200 hertz. So they will observe something greater than 200 hertz, maybe like 250 or 300 hertz. And then someone who's behind is going to hear something less than 200 hertz. So maybe 150 or 100 or something, right? So we can see there that listener number one, the source is moving away from the listener, which means my wavelength increases, my frequency decreases, and the observed pitch is going to be lower, right? Because of that frequency. Listener number two, source moves towards the listener. My wavelength becomes shorter or decreases. My frequency then increases, and the observed pitch then is going to be at its highest or becomes higher. All right. Then we need to look at, in this case here, how we can use the equations. Remember I told you about that equation, if L is equal to V plus or minus VL over V plus or minus VS, right? This is how we can apply it. So if we've got the source moving away from a stationary listener, in this case here, right? So my VL is 0 in this case. The equation looks like this. FL is equal to V over V plus VS. Why is it the case? Remember, because it's going to be plus VL. And in this case here, VL equals 0. So we literally can just remove that and leave the equation like this, right? If the source is moving towards the listener, right? In this case here, again, the listener is still got no velocity. The difference now here is our signs change. Here it was basically plus 0, not plus 0, sorry, it was going to be minus 0 at the top, plus at the bottom. Now here we're going to have plus 0 and minus at the bottom, right? And then if the listener moves towards the source, in this case here, when the listener moves towards the source, then the velocity of the source is 0. So here my Vs is 0, so this is going to be minus 0 in this case here, right? And then we can see finally the last one, where the listener is moving away from the source. Again, my velocity of the source is 0, and then this was going to simply be plus 0 here at the bottom. So if you remember the original equation, right, for Doppler effect, it looks like this. There's a plus minus, right? Now, if the source and the listener are moving away from each other, right, when that happens, you expect a lower frequency, meaning if it's going to be away, you're going to want to choose at the top minus, at the bottom plus. That's for away. If they're moving towards each other, you're going to have a plus at the top, minus at the bottom, right? That's very important for this particular equation here, right? So when they're moving away, you know you're going to get a lower frequency. So we want a smaller denominator, smaller numerator, bigger denominator, minus plus. If they're moving towards, plus minus. That's how we basically do it, right? Think about if you move away from your loved ones, it's a very negative thing. So you put negative at the top. The first feelings you feel, the feelings right at the top are very negative feelings. If you're moving closer or towards your loved ones, you have very positive feelings that you're going to feel there. Okay, cool. Someone says we didn't get the document last time on the channel. Can you please send it to us at the end of the lesson? I definitely will. I did share it in the channel, Chantal, the link that's there, but I will share these ones in our WhatsApp channel. For those that are not in our WhatsApp channel, we'll post the link now. Please join the WhatsApp channel. We do a lot of updates there, and I'll share all my lesson notes in the WhatsApp channel as soon as we're done. Right. Then Ratlegile says, Sir, show the formulae for listener moving away and moving towards. You moved too fast. So I'll go back to Ratlegile, right? But what I want you to think about here is I'm giving you the shortcut, right? The equation looks like this. How do you adjust it? If they're moving away from each other, whether it's the source or the listener, doesn't really matter. What you want to do is, if they're moving away, I'm going to have a much lower frequency when they're moving away from each other. Lower frequency means I'm going to have minus at the top, plus at the bottom. How I said, you must think about it. If you move away from your loved ones, what is the emotion that's at the top of your mind? It's going to be a negative emotion. You're going to be upset. You're going to be sad. You're going to be mad. You're going to cry. So when they're moving away, think top of your head, you're going to have negative emotions, right? And then if you move closer to a loved one, what's going to be top of mind, right? If I'm closer to a loved one, I'm going to have positive emotions, right? I'm going to be happy. I'm going to be excited. I'm going to be looking forward to it. So away, negative, towards plus, and the bottom will always be the opposite of what the top was, right? That makes sense. Okay. Then I'll quickly go review the ones we were looking at there. But if you understand what I showed you here, you should be good. But let me quickly recap it for you because you asked me, right? The ones you wanted to see are listener moving away and moving towards. So let's see. With the listener moving away, my velocity of the listener becomes 0, right? So again, when they're moving away, what's the emotion? It's a negative emotion. So at the top, we get that minus and minus VL. VL is 0. So it ends up just being V over V plus VS. That's how it is there. And then here, you've got the source moving towards the listener. Again, the listener is going to be stationary in this case here. Moving towards, getting closer together. When you move closer to your loved ones, happy emotions are always top of mind. So my top will be positive, right? So it'll be V plus VL. My VL is 0 anyway, and the bottom will be negative. The bottom is always opposite of whatever's on top. Then we have the listener moving towards the source. In this case here, my source is 0. And if I'm moving towards your loved one, positive emotions. Top of mind, always positive. So the top is going to be positive there, bottom is going to be negative, and VS is going to be 0. And then finally, if I've got the listener moving away from the source, when you move away from your loved ones, top of mind is always a negative emotion. So the top is going to be negative, the bottom will be the opposite. And the source is not moving, so my VS will be 0 in this case here. So when you look back at this, we can clearly see that this is going to be moving towards, and this is going to be moving away, right? That's how we basically go through that. Okay, then when we're thinking of our applications, right, of the Doppler effect, so we've got echolocation, right? Echolocation is how bats and surprisingly blind people navigate. So if you've ever seen a blind person with a stick, right, you'll notice that when they have that stick, they don't just like put the stick in midair and just sort of try and feel their way around. What they do is they tap that stick. They go tap, 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 tap. Because what they're doing when they're doing that tap, the sound will travel and sound will come back. And they are very well attuned to how the sound comes back. And they can use those sound waves to determine what's in front of them and what's around them. They can kind of echolocate. Bats do the same thing. So bats make a noise, that sound. I can't make the sound myself, but it's a very high pitched sound out of their mouths. And that sound is going to travel there and come back, right? And with that sound, they can tell whether an object is moving closer or further away from them. And they can then usually see without their eyes. They can almost see with their ears. That's echolocation. Then I mentioned speed guns as well, right? It's those speed cameras that we have in South Africa. They are radar guns or speed guns or speed cameras. They use the Doppler effect as well. And basically, dependent on the frequency of light that comes back after being emitted, you can tell if an object is going away or towards you, and how far away, and how quickly away or how quickly towards you, based on how much that frequency or that apparent change in frequency is going to be. Then you also have the ultrasound, like I've mentioned before. Ultrasound, you can use it in hospitals to check and scan for babies or scan for tumors. You can also use ultrasounds, like the submarines. They use sonar as well to go and see the ground underneath the water, essentially. Those are some applications of Doppler effect. There's lots more applications. Do your research, go and try and say, what else can I use to, what applications are there of the Doppler effect, right? Don't use ChatGPT for your assignments, but for things like this, go find out. Spend some time online and see what are some applications of the Doppler effect that you can use in your exam that will be accepted. All right. Then we come and talk about the Doppler effect of light, right? So remember, light is also a wave. It's a particle and a wave. And we can also have Doppler effect of light. Okay, sorry, someone's asking there. Sandika's asking, how can we get the recording of this meeting? Sandika, when we're done with the session, normally we will post them to our YouTube. So all our previous recordings will be on YouTube. If you look in the chat, there's links to our TikTok, Instagram, our YouTube, and our WhatsApp channel. So if you go to our YouTube, you'll find previous recordings of the lessons we've had. But I recommend you stay so that you can actually ask questions if you need to, right? Awesome. Now, red shift and blue shift. So the Doppler effect applied to light. Now, if you remember the light spectrum, right? Let me quickly try to find a picture of the light spectrum. Um, okay, so if you think back to the light spectrum, you'll remember Roy G. Biv or anything like that. So here's a nice picture of the light spectrum. Let me just make this bigger. Sorry, let me quickly just cancel all of these cookies. Okay, so here's the light spectrum. Now, when looking at the light spectrum, we can see at the bottom, they show us the 380 to 440 nanometers. That's the wavelength, right? So violet light is between 380 and 440 nanometers. Up at the top there, you've got red, 625 to 740. Beyond, just after violet, you get blue, that 440 to 485. Now, when we're talking about red shifting and blue shifting, what we mean is that the light tends to shift in the direction of red. Not that the light will appear red. So green light will look a bit more yellow. Cyan light will look a bit more green. Blue light will look a bit more cyan. Violet will look a bit more blue. That's what we call red shifting. Not that the light will look red. And something that's going to be blue shifted means it's going to shift to the side of blue. Red light could look orange. Orange light could look yellow. Yellow could look green. Green could look cyan. Cyan could look blue. Blue could look violet. It just means you're going to shift in the direction of blue or blue has the shorter wavelength, 440 to at 440, 485. Now, remember, wavelength and frequency are inversely proportional, right? So when something's moving away from me, right, longer wavelength, it's going to appear more red shifted when it's moving away from me. When it's moving towards me, shorter wavelength, it's going to appear more blue shifted, right? And that's how we then determine it. So in sound, we have high pitch, low pitch. That's how we determine frequency. In light, we've got red shift, blue shift. So again, a high pitch is a shorter wavelength, blue shift. Low pitch, longer wavelength, red shift. That's how you must think about the Doppler effect of light, right? So when you can see here, you'll see that these two, so this is going to be a light spectrum, and this will be a light spectrum of the same thing, just moving differently, right? So this spectrum here and that spectrum are the same thing. Notice how in the second instance, this line has moved to the right. That's moved to the right. That's moved to the right. So my spectrum has now shifted towards the red side. We say that that light has red shifted. That's what that means, right? It's moved to the red side of the spectrum where ordinarily it would have been here. Now it's sitting a little bit to the right-hand side, meaning whatever was emitting that light is definitely moving away from us, or we are moving away from that thing. Because when we see it, it appears red shifted. If we were both stationary, this is how I would see it. That's very important, right? Kopano, please stop annotating the screen. A single warning, next time it happens, I'm going to ask our admin to remove you from the lesson. Okay. So that's how we then see blue shift and red shift. So again here, as the light source moves away from the viewers, the observed wavelength increases. And when wavelength increases, it tends to shift towards the red side of my spectrum. And we then say that the light is red shifted. But the very same light that we can see here, if it were moving towards us, it would appear like this, where it's the same type of light, but it's now on the towards the blue side of my spectrum. And as the light source moves towards the viewer, the observed wavelength decreases, right? And when it decreases, it moves to the blue side of my spectrum, and we can therefore say that it is blue shifted. That's how we then can tell when we're looking at things in the distant sky, whether they're coming towards us, going away from us, because of the red shift or blue shift. Oftentimes we know what certain light should look like. And this absorption or emission spectrum, right, that we're looking at here. So this would be an emission spectrum. It's how light is emitted from certain elements, so hydrogen or oxygen or whatever. And scientists know what it's supposed to look like. So we know the standard one, this one. Then when you see it look like this, you're like, something's wrong there. It doesn't look in position. It looks more red than it should be, which means the thing that emitted that is moving away. Or you'll see it look like this and say, I know this pattern. This pattern is for whatever, helium. But helium is never in this position. It's normally more right. If it's moved towards blue, it's blue shifted. It's probably coming towards us. That's how they detect those things. Which finally then brings us to the red shift that we perceive. So the presence of redshift in light from stars tells us that the universe is expanding. Because what happens is that as we look around the universe, light from stars that's coming to us, we expect it to look one way, but the majority of stars are redshifted to us. And whether you look left or right or up or down or whichever direction, most stars are redshifted. And that tells us, oh, okay, this must mean that everything is moving away from us. And when everything is moving away from us, the thing that makes sense is to say that the universe must therefore be expanding. Right. So when they ask you about the how we know the universe is expanding, you then say, well, the presence of redshift from light from stars all around us tell us that the universe is expanding. Because when light is redshifted, it usually refers to the fact that the object that's emitting that light is moving away from the object or the person that is perceiving or seeing that light. Okay, hope that makes some sense to you guys. Let's have a quick look at the simulation I want us to look at for the Doppler effect. So I use a site called JavaLab. Please just take note of it. It's a really cool website. Some people also use Fed simulations, but I like JavaLab. It's pretty simple. It's nice and chilled, right? And just to help us better visualize the Doppler effect. So I'm going to open up this little simulation here, and I hope the sound is going to come through. Okay, it'll just load a little bit. Give it 2 seconds. There we go. So when we're looking at the simulation, on the left-hand side, you will see an ambulance that's going to move towards a listener. So in the middle of our screen, we've got our listener there. Let's call her Buitepo, who's our listener. Now, if I choose for the ambulance to move at this speed, the sound waves go. And then the minute they hit the listener, we can start hearing that sound, right? I don't know if you guys can hear the sound. Someone please just confirm if you can hear the sound of the ambulance. Okay, perfect. Now listen carefully at what happens when the ambulance passes the listener. Right? So that's one of the things that you guys will often hear, right? So as you go, so when it's coming towards us, we hear it as a very high pitch. Woo, 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 woo. And then when it passes, the pitch goes down. Woo, 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 woo. Because the wavelengths in front of the ambulance are compressed. It's emitting it and moving closer, emitting it and moving closer. So we have compressed wavelengths in front and we have expanded wavelengths behind. So high frequency in front of the ambulance when it's moving towards us. When it's moving away from us, we have a low frequency. Nice little simulation for you to have a look at. And you can see if I change the speed and make it move at double the speed, a change in pitch is going to be even higher, right? So I know in the simulation it's quite exaggerated. A lot of you who've sat when an ambulance or a police car drives past, you'll hear it. It's not as exaggerated, but this is just to give you the full effect to see how it really goes, right? Okay. I see there is a question here. So Sandika says, so it appears more on the red side of the spectrum. That is when something is red shifted, 100% Sandika, right? And someone says, Liema says, I think it's because the wavelength increases to the red shift, which means that the universe is expanding. Yes. So most light that we'll see it will appear on the more on the red side compared to where we know it's supposed to be. And that's because the wavelengths have increased and have expanded. And that tells us that they're moving away from us. And that is definitely a sign that redshift all around says the universe is expanding. Kaylee says, so is pitch and speed directly proportional? Okay, let me think about that question, Kaylee. It's a very good one. So the pitch is more to do with the frequency. So there's a lot of factors that are there. The faster you move towards me, yes, the higher the pitch will be, but the higher the pitch change will be. But when you're moving away from me, the faster you move away from me, the lower it is. So it's not always directly proportional. But the faster you are, the more dramatic the change is. So if the perceived pitch is much higher, it's usually because it's moving very quickly towards me. If it's moving very slowly towards me, the perceived change in pitch is not going to be as dramatic. So I think it's not necessarily the speed at which that is directly proportional to the pitch, but the speed is proportional to the amount of change. So whether it's going to be a high pitch or a low pitch, it becomes a lot higher if it's moving fast towards me and a lot lower if it's moving fast away from me. I hope that helps, Kaylee, answer your question there. Okay, cool. And that's my little quick summary on the Doppler effect. We've got an hour, 10 minutes to do some questions, and I think we'll hopefully be able to get through a lot of them. And what I'd love to do is get through. There's a question I did for the winter school that I'd love to redo with everyone today, but we'll leave it for last. I've got some new questions. I don't want to give you guys the very same lesson you've seen before, right? I want to try and always give you something new when we do a different lesson. Okay. Kaylee says, okay, thank you. It's my pleasure, Kaylee. All right, so let's first jump straight into our first question, which is question 6, right? So question 6 is, and please, guys, as a note, try do these questions with me. So take out paper, take out a calculator, sit and do the questions with me. That's the best way to learn, right? Don't just sit and listen to me give answers. Try the questions yourselves. I'll try take it slow and give you guys enough time to answer the questions there. All right. So let's start with the first one. 6.1 says, a stationary sound detector placed at a certain point records 520 sound waves per second from a moving sound source, which emits sound waves of frequency 480 hertz. Write down the frequency of the sound waves that the detector records in hertz. Put that answer in the chat quickly for me. So what frequency was detected by the detector? Give the answer in hertz for 6.1.1. Put your answer in the chat as soon as you've got it there. This one is 1 mark. It doesn't need any calculation. You should be able to give me the answer directly. Write down the frequency of the sound waves that the detector records in hertz. I'll read the question again from number 1. A stationary sound detector placed at a certain point records 520 sound waves per second from a moving sound source, which emits waves of 480 hertz. I want you guys in the meeting chat to pop your answers in there. What is the frequency that was detected by that detector? Give your answer in hertz. Thanks, Emma, for your quick fingers. Thanks, Tato. Thanks, Delcy. Thanks, Karabo. Thanks, Tiri. Thanks, Katie. Thanks, Gabelo. Thanks, Unalina. Okay, thanks for the answers. I'll give you guys 20 more seconds. Please read the question very carefully. Thank you for all the quick fingers there. Okay, 10 more seconds. If you haven't put your answers in, quickly pop them in. 5, 4, 3, 2, 1. Okay, let's quickly look at this one together. 6.1.1 says, write down the frequency of sound waves that the detector records. Let's go back and read the question. The question then says, a stationary sound detector, that's what we're looking for, placed at a certain point, records 520 sound waves per second, right? So 520 sound waves per second is going to give us the answer because it means we are recording 520 hertz. Remember what hertz means, right? Hertz means the number of things happening per second. So if we recorded 520 sound waves per second, that's what was detected. The frequency is 520 hertz. The 480 hertz is what was emitted. So this is what the sound source emits. That's 480. But we asked for what did the detector record? So what was heard? What was heard or detected was 520 sound waves per second, which is 520 hertz. Okay, very important to note the difference between those two things there, right? Very few of you guys got that question right, but I hope what I'm saying makes sense. If it makes sense, please give me a dancing emoji, fire emoji in the chat. But I want to make honorable mentions. Lebuhile, you got the question right. Honorable mentions, I think was like about 3 of you guys. And I was looking through the questions. Wait, Lebuhile, you might be the only one. I'm quickly going to scroll through Lebuhile, yes. Hey, everyone else said 480. And it was a little bit of a trick question. In that case, actually, Lebuhile, you were the only person that got that 520. Well done. I'll give you a dancing emoji in the chat for that. Let me quickly try and type it in there, right? Thanks, Lema, for your dancing emoji. Yeah, so everyone else, as long as you understand what that is right now, you can jump in there with our celebrations. Because what does that mean? So, guys, one of the things I'm going to remind you is I love getting things wrong. Getting things wrong is fun. I know it makes you guys stress. Don't stress when you get things wrong. So you get things wrong in class. That's good. That's perfectly fine because this is where you get a chance to learn and get corrected. Where you don't want to get things wrong is in your exam. So when you're sitting in the lesson with me, get it wrong perfectly. Don't even be shy to give me an answer, right? Because if you get it wrong, it allows me to see where you have got misconceptions and I can correct you. If you keep quiet and don't give me your answer, I can't fix your misconceptions. And for you to get the most out of these lessons is to participate, give me your answer so I can help correct you. Thank you for everyone who's celebrating in the chat. You guys are really, really awesome. Okay, let's move on to the next question. The next question is going to be 6.1.2. 6.1.2 says, define the phenomenon which explains the change in frequency observed. So I want you guys, before you do the definition on your paper, in the chat, tell me what that phenomenon is called. When a listener hears a different frequency to what was actually emitted, right? Because there was movement between. Thank you, Sandika, for there. Thanks, Kifilwe. Thanks, Liama. Perfect. Okay, cool. You guys know what it is. Then the question says, define that phenomenon. So you guys told me what the phenomenon is. It's the Doppler effect. Well done. Now I want you to define the Doppler effect. Okay. I'll give you guys 30 seconds to write it in your books. And then I'll give you guys the answer just now. We read that definition about 3 times as we were preparing. So quickly write down the definition in your books, and then I'll give you guys the answer in the next 30 seconds. Guys, please don't annotate on the whiteboard. It's very distracting to everyone else who's in the class watching. Okay, 10 seconds left, and I'm going to give you guys the answer for 6.1.2. Thanks, Licebo. So we got 2 very free marks there. Right, the 2 very free marks we have. Okay, is that the phenomenon known as the Doppler effect is the change in frequency or pitch observed or detected by a listener because the listener and the sound source have different velocities relative to the medium of sound propagation. Awesome, guys. If you got that right, give me your celebrations in the chat. If you didn't, but now see where you went wrong, jump in, let's celebrate because it means you're learning, right? It means we're doing well. We're going to be doing really well when these prelim exams come. Thanks, Kabelo, there for your answer as well. Fantastic. Cool. Thanks, important Delcy, for your guys' celebrations and Asanda as well. Okay, let's jump on to 6.1.3, right? 6.1.3 says, is the sound source moving towards or away from the observer? Let's quickly go back to the question. Remember, we detected, so the listener heard or we detected 520. What was emitted was 480. So the question there, is the source moving towards or away from the observer? Thanks, Chantel, for your quick fingers there. Thanks, Gift for quick fingers. Thanks, Raphael. Thanks, Kush. Thanks, Tepang. Thanks, Masefo. Okay, there's a lot of answers coming in. Thank you to all of you guys coming in there. Thanks, Larato, for even giving for your explanation. Thanks, Tepang, Mapula. Thanks, Nangomso. Thanks, Natisha. Okay. If you haven't got your answers in, I'll give you 10 seconds. For now, in the chat, write towards or away. In your book, you can put the full explanation. Thanks, Gift. Thanks, Misle. Thanks, Dimpo. Okay, quickly put your answers in. 5, 4, 3, 2, and 1. Okay, so let's have a look at it. Remember, if it's coming towards me, I'm going to get a higher pitch. If it goes away from me, I hear a lower pitch. Okay, cool. So 480 was emitted. 520 is what was heard. So I heard a higher pitch. If I hear a higher pitch, it must be coming towards. So the right answer there is going to be towards. Let me quickly just highlight this. So towards is our correct answer. And what's the reason? Why do we say it's moving towards? The reason is that the detected frequency is higher than the source frequency. You can quickly put that answer in there. The detected frequency is higher than the source frequency. Okay. Hope that makes sense, guys. If you got the right answer, you know the drill. Jump in, whatever you're going to use to celebrate. Give me something different to dancing emoji now. Thanks, Abongile. There we go. Give me a rocket emoji. Let's get creative. Let's see the most creative emoji we can get in this one there. Thanks, Asanda. Thanks, Karabo. Okay, fantastic. And if you didn't get it right in your book, but you see where you went wrong, jump in. Let's celebrate. It means you're learning. It means you're going to do better in your prelims than you did in your June exam. So that's a good thing. Okay. All right. That's some contextual questions. Now let's start doing calculations, right? So 6.1.4 says, now calculate the velocity at which the sound source is moving. Take the velocity of sound as 343 meters per second. So we need to calculate now what speed the sound source is moving. We need to do that calculation. And then they told us that the speed of sound in air as 343 meters per second. So let's first write down our equation, and then we're going to then unpack that equation. So step one, write down the equation. The equation is going to be as follows. Okay, so we've got the frequency of the listener is equal to V plus or minus VL divided by V plus or minus VS times the frequency of the source. Now remember, what I said was, let's first figure out, is it moving towards or away? Towards, we know we're going to be happy. It's going to be plus at the top, minus at the bottom. That's the first thing there, we know. And then already we're looking for the velocity of the source, right? Which means we know that our listener isn't moving at all. Our listener is going to be zero. That's the first thing we'll do. So let's write the final version of that equation there. So we know that the frequency of my listener is equal to V plus or minus doesn't matter. It's going to be plus 0. We can leave that out. Divided by, at the bottom, V. Is it plus or minus? It's going to be minus. So we can simply just put there minus Vs, right? Times the frequency of the source. Now I know which version of the equation I'm going to use. The next step, I can then start substituting. So let's substitute the values we're given. So we're told that the frequency of the listener, the observed frequency, is 520 hertz. We saw that. So let's substitute that in there. So when you substitute, I'm going to go up here. So that's going to be 520. That's the frequency of the listener, is equal to V is the speed of sound in air. And there we were told it's 343 meters per second. So that'll be 343 divided by V minus Vs. So V again, that's 343 minus the velocity of the source. That's what we're looking for. It says there, calculate the velocity at which the source is moving. So we leave Vs exactly as it is, times the frequency that was emitted, the frequency of the source. At the beginning, we can very clearly see there that it was 480 hertz that was emitted by the source. So let's quickly plug that into our into our equation, 480, and now we can solve for Vs. So what I'm going to do is make Vs the subject of the formula, and then you can plug that into your calculator and solve, right? So in this case here, I need to divide both sides by 480. So I'm going to have 520 divided by 480, right? And that's going to be equal to 343 divided by 343 minus Vs. I can either at this point cross multiply, or I can flip both fractions to get my Vs towards the top, right? So you'll do the maths in between. Remember, for a science paper, you don't get marks for the maths. You get marks for the equation, you get marks for the substitution, and you get marks for the final answer. So let me quickly get to the final version of what Vs should look like, and then you guys can plug it in your calculators. Essentially, you'll get Vs is equal to, at the top here, you're going to get 480 times 343 divided by 520 in that case there. and then minus 343. So it'll be minus this plus 343. So something like that. A lot of you guys have put the answers in the chat already. Reabaka, Tisetso Kabelo, um, Musilancha as well. Mihle Gift, Nangomso, Liema, well done. Okay, cool. You guys all popping that answer in there. If you're still busy, don't feel pressure, don't panic. Take your time. We're going to go through these questions nice and easy, right? But you guys have got some good answers there. The final answer is correct there, 26.38 meters per second. Okay, Balentla has a really good question. So may I ask, is the velocity, I'm assuming you talk about the velocity of the speed of sound in air. Is it always 340 meters per second or it changes sometimes? 100%. At the beginning of the lesson, I did make mention of that. The speed of sound in air is not a constant. It depends on the pressure, it depends on the density, on a lot of factors. So often they will give you the value. So it'll usually be between 330 and 340 something, 350, somewhere there. So always look for the value that they give you. Don't just assume it's 340. Mbalente, that's a very good question. Okay. Then once we've crunched everything, our final answer should then be 26,38 meters per second, right? Remember, your unit's very important. That's how you guarantee to get all your marks in this case here. So for this question here, to get all 5 marks, you need to be able to write your equation effectively. You need to do your substitution effectively. So you'll get a mark for that. You'll get a mark for this step in between and a mark for that. And you'll get a mark for your final answer, which is how you get your 5 marks. Super simple. Guys, I want you guys to note as well, right? This question is out of 15. We haven't done anything difficult so far, right? And already we've got 10 marks out of 15. That's 66% of this question. And we've done nothing difficult. And that's the thing I always like to show learners, that you can get 40% in an exam without even trying. You can get 65% in an exam without doing any difficult question. You can literally get 65%. 65% means you qualify for a STEM degree, like you'll get into engineering if this university isn't too full. Trying to get into engineering, you better have marks in the 70s, but 60s sometimes you can get in. So without trying too hard, just by applying yourself at a very basic level, equation, substitution, answer, and definitions, you can get 60% for a particular test. So it is very possible, guys. Please, if you haven't been getting 60s up until this point, don't panic. Just take it step by step. You now know what you need to do. If you join all of our lessons, we will show you step by step. Go watch the previous lessons and we'll take you step by step through these problems. And you can see that it's actually super easy to get and land 60% in a science exam. And if you try and put in some effort, that 70 is not out of reach, that 80 is not out of reach either, right? It just requires a little bit more effort. Okay, now we're going to need to think a little bit beyond this point. So to get to 60%, 66% here, 10 out of 15, we got there without having to think too much. The next step, we do have to think at this point now, right? So the part where we need to think is going to ask us the following. 6.1.5 says, how would the wavelength of the sound waves produced by the sound source change if the frequency of the sound waves become higher than 480? So think about that. How would the wavelength change if the frequency is higher than 480? Write down only increase, decrease, or stays the same. So in the chat, just write down again there, increase, decrease, or stay the same. And I will minus points for whoever tries to be funny and writes crease. Thanks, Liam and Balentle, for you guys' quick fingers there. Thank you for all the quick fingers there. I'll give you guys 10 more seconds. Nkele, please don't annotate the screen. Okay, 5, 4, 3, 2, 1. I'm gonna start putting dancing emojis now in here because you all got the answer right. You guys are awesome. I'm gonna put a crazy amount of dancing emojis there. Let me pop that in the chat for you guys there. Okay, because you guys all got it right. Clara, that's a very interesting one to celebrate. Okay, I'm seeing some very creative celebrations there. I'm loving it. I'm loving it. I'm loving it. Thanks, Christina. Thanks, Dimpo. Thanks, Bilonhle. Thank you. Thank you, Oguhle as well. Okay, so the answer in this case is going to be decrease, right? So decrease is the correct answer. Let's quickly circle the correct answer. I'll just write it out here. Decrease. What is your reason? So remember that frequency is inversely proportional to wavelength, right? But particularly if speed is kept constant. And that's the case because the speed of sound in air remains like they gave us here, 343 meters per second. So frequency and wavelength are inversely proportional. So now we're at 12 out of 15. You try to work out how much that is, but that's definitely for this particular question. If you've gotten them all right so far, that's 80%. That's an A for this question, right? Okay, so let's quickly move on to the last two parts of this question. And the last two parts of the question talk about now the Doppler effect of light, right? So in this one here, we see that the spectral lines from a distant star are observed, and they're observed to be red-shifted. Very important. Now, explain the underlined term. So they're asking us to explain what does it mean, right? And Dogoza, please don't annotate the screen. You are causing disruptions. What does it mean for something to be red-shifted? Okay. And like I told you guys, remember, don't say the light is going to be red in color, right? What does it mean to be red shifted? Okay. You can type the answers in there as well. I'm going to quickly put my answer down there. Okay. So when light is redshifted, what we're looking for there is that light from the star is shifted towards the longer wavelength. So towards the red side or the red end of the spectrum, right? Which indicates that the star is moving away from the Earth. So when we are observing it, they have to put there that it indicates the source of light is moving away from the observer 100%. So what I want you to add there to get both of your marks is not just that it's moving away from us, but you must make reference to the wavelength, right? To say the light is shifted towards the longer side of it's shifted towards the red side of the spectrum, or the wavelengths are longer. Make reference to the wavelengths and then say, how does that now talk about the movement of that particular object? But thanks very much, Larato, for your answer there. Sigo says the shift in the spectra of distant galaxies towards the red end of the spectra, 100%. And then you must add, what does that mean about the movement of that object? So yes, it's shifted towards the red end of the spectrum, then it means that it's moving away from the observer, or in this case, the Earth or us or whoever's watching. Thank you guys, Larato and Sigos, there for your answers. You guys are awesome. Okay, let's quickly do our last one. 6.3, write down one application of the Doppler effect in the field of medicine. Okay, I'll give you guys 15 seconds to write down an application of the Doppler effect in the field of medicine. We went through a few of them together. There we go. So some of the answers that are coming through: ultrasound, blood flow meter to check the heartbeat of the fetus. Okay. Okay, we've got them there. Doppler flow meter, ultrasound to determine the heartbeat of a fetus as well. Measure heart rate, 100%. Okay, perfect, guys. I'll give you guys 5 more seconds for those there. I see there are some hands that I might not have noticed before. I don't know if that was a reaction. Okay, I don't see hands right now. Okay, so we should be good. Okay, But thank you for all those answers, 100%. So ultrasound, um, devices that measure heart rate, the flow, what someone said, the Doppler flow meter, definitely going to be there. So the only thing I'd say, so people who said to check the heartbeat of a fetus, so that is it's what we do. So I'd say to be safe, mention the device. So say your flow meter, the Doppler flow meter, say ultrasound, and then you can then say those are used to check blah 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 blah. So mention the device to just guarantee all the marks, right? I wouldn't say you guys are wrong, but the example I always give is you don't want to give your examiner any chance to mark you wrong. So try and be as explicit as possible to try and save yourself from losing those marks. But you guys are awesome. Okay. Yeah. And then I saw. Oh, the last two said speed guns, and then Balente said it said in medicine. 100%. Thank you, Balente, there. Very important because it's specified that it must be in the field of medicine. Speed guns are not necessarily there unless if you try to be clever and you tell them that um, ambulances maybe tripped a speed camera and ambulances work in medicine. You can try be clever, but don't try be clever for your examiners, right? Um, okay, awesome. So as we move now, that's the end of the first question. I'm going to pause for any questions. If anyone wants to ask a question live, put a hand up. I'll give you a chance to speak. And then if everyone's comfortable, we're going to jump on to another question altogether. Right. So I've got, like I said, I've got three questions for us to go through. I'm pretty sure we'll do all three of them, but I'll pause for questions. I'll give you guys 2 minutes. Put your hand up and I'll let you unmute and speak and ask your question live. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2. Everyone seems to be happy. Fantastic. Okay, if you're happy for me to move on to the next question, give me a thumbs up emoji, give me a running emoji so that we can move on to the next question. Okay, thanks a lot, Wheeler there. There's thumbs up reactions in the chat. Fantastic. Okay, let's move on to the next question. Okay, the next question is as follows, right? The question then says there, the siren of a stationary fire truck emits sound waves with a frequency of 1,800 hertz. A car traveling on a straight horizontal road at a constant speed of 30 meters per second passes the fire truck and continues at the same constant speed. State the Doppler effect in words. We did that in the first question, so I'm not going to dwell too much on that one. The definition is there. We can see it. I'm going to jump onto the next part of this question, right? 6.2 says, how does the pitch of the siren heard by the driver of the car change when the car is moving? State only increase, decrease, or remains the same. So how does it change? 6.2.1, when it's moving towards the fire truck. Does the pitch increase, decrease, or remain the same? Quickly put that in your chat, 6.2.1. So write down 6.2.1 and then say increase, decrease, or remain the same. I'll give you guys 2 minutes to put that in the chat. How does the pitch of the siren, as heard by the driver of the car, change when the car's moving towards the fire truck? Thanks, Ryan. Thanks, Liama. Thanks, TD, for your quick fingers there. Thanks, Asanda, for actually listening to what I said you must do. Write 6.2.1 and then your answer. Um, I can see, Asanda, you're going to be our top student there for reading the question very carefully. There's a story, I don't know how true the story is, um, where I don't know if it was a lecturer or a teacher was testing how well learners read their paper. And somewhere like in the paper, he just wrote like in like a long story, and then said, to get full marks for this paper, write your name, leave it blank, and submit it. And people didn't actually read it carefully. And I think it was like only like one person who actually saw that and did it and actually got full marks for the paper because they actually read this thing thoroughly. Don't know how true the story is, but it's a story that I heard. Okay, let's quickly look at the answers. We've got a few remain the same. We've got a lot of increase. A lot of increase, a lot of increase, mostly increase, mostly increase. Okay, perfect. We've got a mostly increase and a few remains the same. All right. So for 6.2.1, right? Remember, when I'm moving towards the fire truck, what I expect to hear, right, in that case there is going to be, sorry, an increase in frequency. When moving towards, my wavelengths are shortened, my frequency goes higher, my pitch is going to be higher as well. So for 6.2.1, I do expect an increase. Where those celebrations in the chat if you got it right. If you didn't get it right but see where you went wrong, you're more than welcome to join in the celebrations. You learned something new. It's a mistake you won't make in your exam, right? 6.2.2. How does the pitch change when the vehicle now moves away from the fire truck? Choose between increase, decrease, or remains the same. And then for those that wrote to remain the same, please note that the pitch will only ever be the same if both objects are stationary. So if there's no movement at all, the listener will hear exactly what's being emitted. But if there's relative motion, there will be a pitch change either up or down, right? So the pitch will be up or frequency will be up if they're moving towards, it'll be down if they're moving away. Okay, thank you. I see a lot more 6.2.2s coming in there. A lot of good answers. Decrease, 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 decrease. Okay, I'll give you guys 5 more seconds to finish off putting your answers. Okay, 5 seconds. 4, 3, 2, 1. And you guys all got it correct. I'm gonna throw you guys some mind-blown emojis in the chat there because I'm mind-blown. You guys got it all right. The correct answer is decrease. As it moves away from the ambulance, the wavelengths get longer and longer, which means my pitch and my frequency will then decrease. Well done, guys. You guys are amazing there. So that's decrease. Sorry, let me fix this here. All right. 6.3. It says, calculate the frequency detected by the driver of the car as the car moves towards the fire truck, right? Calculate the frequency as the car moves towards the fire truck. Take the speed of sound in air to be 330. Let's do our same thing we did before. Start by looking at the equation, right? So the first thing, let's put the full equation down. In your exam, you don't have to do this, the steps that I do, right? I just like doing it so that I can see, but you must put an equation. Very, very important. Okay, frequency of the listener is equal to V plus or minus VL over V plus or minus Vs times the frequency of the source. Now we said it's moving towards. Remember, when you come towards your loved ones, you are going to have top of mind positive emotions. So we know there already we're dealing with plus minus. Let me put this up here, plus minus. And we know that the car is moving towards the truck. The truck is stationary, right? And we know that here that the siren of a stationary fire truck, so the source is stationary, so velocity of the source is going to be 0 at that point there. That will then help me determine the final equation, which is frequency of my listener equals V plus VL over V times the frequency of my source. Now I've got the proper equation. I can substitute my values and then get an answer, right? Let's quickly do that there. Frequency of the listener is what we're looking for. They said what is detected by the driver. So I want to find FL. Let's now find everything else. So I'll leave FL exactly as it is. V, which is the speed of sound in air, we were told to take that as 330. So that'll be 330 plus the velocity of the listener. The listener is the car. And we were told that this car is traveling at a constant speed of 30 meters per second, right? So we'll put that there as VL is 30 meters per second. At the bottom, we've got our V, which is the speed of sound in air. That's going to be 330. Frequency of the source, what was being emitted? If you go back to our question, you'll see that it says a sound of 1,800 hertz was being emitted. Let's put that into our equation. So times 1,000 800. Then you guys can quickly pop that into your calculator and give me an answer for what will be observed. Thanks, Rabaka. Thanks, Clara. Umulimo Gift, Tiseto, Tato, Cabello, Inati, Mihle, Sigos. Thank you guys for your answers. There, I'll give everyone else 20 seconds to finish the calculation, and then we'll look at the answer together. Okay, 10 more seconds to get your answers in. Guys, just a reminder again, not to annotate the screen. 5, 4, 3, 2, 1. And you should get a final answer of 1,963. Oh, my 3 is looking weird there. 63,6 hertz, right? If you got that correct, please jump there in the chat and celebrate. I think when I look at most answers, they all look correct. Let me just make sure if I need to help someone out there. Kifilo, you forgot your units. Katleho, you also forgot your units. Mitle forgot your units. Okay, don't forget, if you leave those units out, you will lose marks, guys. But thanks for the celebrations. You guys are awesome. But everyone else got the magnitudes correct, which is fantastic. You guys are great. You guys are great. Okay. That was 6.3. 6.4 now says, let me quickly make a bit of space here for us to work. It says, sketch a graph to show the frequency of the siren changes as a function of time as the driver approaches, then passes the fire truck. No numerical values are required. So now we have to then draw a graph that shows how the frequency changes over time, right? So the first thing I need to do is draw my axes. So let me quickly do that. Okay, wait, it's a bit too thick. Okay, let me draw axes first. Okay, so on that, I'm going to have a frequency axis. Frequency is measured in hertz, and a time axis measured in seconds. So we know that as it moves towards, it'll have a higher frequency, and when it moves away, it'll have a lower frequency, right? So in that case there, when it moves towards, it'll have a higher frequency. So let's draw, so you'll have a line that looks like this. This is the part that talks about towards. And then at some point, it will be at the point of the vehicle, and then it'll move away. And then when it moves away, you'll have a frequency like this. So that's all you need. And just sort of to annotate that there, this part here, you don't need to write the part in red, but this is the towards, and that part there is the away. So you have the higher frequency towards, and then the lower frequency away. And somewhere in between, somewhere here, this is like the real frequency, the real emitted frequency, somewhere in the middle of those two, right? Okay, but what you just need here is just draw axes, label them, show that it's initially higher, then it goes down, that's the second mark, and then show that your lower frequency as time increases comes afterwards there. That's the key thing there. So that's all you need to do there for this particular question. I hope it makes sense to you guys. If it makes sense, please give me a thumbs up in the chat. I know I can move on. Sandika says, how do you know which is the X and Y axis? It's a very good question, Sandika. So the question said, sketch a graph of frequency changes as a function of time. right? So frequency as a function of time means that time is the variable that we change, right? It's our independent variable. Our dependent variable is going to be frequency. So your dependent variable goes on your y-axis, your independent variable goes on your x-axis. I hope that makes sense. So based on how the question said it there. And then Carabello said, please explain it again. Carabello, please also tell me which part you didn't quite understand. Remember, I always said saying please repeat is not necessarily a high quality question. High quality questions come with saying, I understand this. What I don't understand is that. Okay. But I'll repeat it just for clarity. So they said sketch a graph to show how the frequency of the siren changes as a function of time, right? So in this case here, as the driver approaches and then passes the fire truck, no numerical values are required. So you start by saying, okay, cool. The key thing that's going to be my independent variable, x-axis, that's time. So it's how frequency changes as time goes by. So I'll start with my frequency. You know that when an object moves towards, be it the source or the listener, whenever they move towards each other, you expect to see a higher frequency. When they move away from each other, you get a lower frequency. The real emitted frequency is somewhere in between. All this question really cares about is what I drew in purple. My notes towards real frequency away are only to help you guys visualize this thing a bit better. You don't need them for your final answer. So I start off saying, well, it's moving towards, so I'm going to have a very high frequency to begin with, right? Once it passes, this is where it passes the object, I'm going to have a much lower frequency. So then I said, the top part is when it's moving towards, the bottom part is when it's moving away. Somewhere in between is the real emitted frequency. These notes here are not required for marks for this question. All you get marks for is your axes and drawing your two lines, making sure that the before is higher than the after. That's the key thing that you get from there. Okay. I hope that makes sense. There's another question from Sandika. Is it a right thing to say that the first variable is the independent variable always? Sandika, it depends on how they set it. So don't always assume the first variable is the independent variable. In this case here, they said, show how the frequency changes, which means frequency was my dependent variable in this case. My independent variable is going to be my time, x, right? So look at how it's going to be. So if you're expecting frequency to change, that is a dependent variable. That's the one that's going to change based on whatever my independent variable is, which is x. And then Tepanang says, is time always on the x-axis? Usually, I don't want to say yes always, but usually time is on your x-axis, right? Time, time can be a dependent variable. So for example, I can say, how long does water take to boil based on the state it was in? So if it was ice format, if it was mixed ice and water or just liquid water, how long will it take to boil? In that case, the time it takes to boil is a dependent variable. And in that case there, if you were to draw a graph, it wouldn't be a line graph. It'll probably be more like a histogram. Time would not be your x-axis. Time would be your y-axis. So there are instances where it's that. So what's important for me there is your x-axis should always be your independent variable. Your dependent variable always on the y-axis. And more in science exams, they're doing more and more experiment, investigation type questions. So it's very important that you know how to read graphs as you do it. Okay. And then Sandika says, thank you. It's quite a pleasure to help you with that question. All right. Then 6.5 is the same question we had in the previous one. Name a medical instrument that uses the Doppler effect. In this case, they talk about the instrument directly. So blood flow meter, Doppler flow meter, sonar, any of those. Okay. So Karabo says, thank you. I was going to draw a straight line. Yo, it's very important. Yeah, I'm glad I could help you with that one there, Karabo. Okay. So quickly, for everyone who's been itching to make a mess and annotate this board, I'm going to give you guys 2 minutes, right, to go crazy on my whiteboard. Tell me In whichever way. You can draw a picture, you can write words. How are you feeling about the Doppler effect right now? Is it a bit easier? Is it better? How are you feeling? Just give me a sense of how you're feeling. You can put anything you want on the whiteboard. How are you feeling about the Doppler effect? Go crazy on the whiteboard for 2 minutes. Okay, yeah, you guys have had a lot of pent up anticipation to just go wild on this whiteboard. Okay. Keep going. I'll give you guys some time to just go crazy. Get it out of your systems. Let's do that. Some of you are just scribbling. I don't know if that's frustration or it's excitement. You must tell me what that is. Let's take a screenshot of this. Turn it into artwork. Okay, 10 more seconds. 5, 4, 3, 2, 1, and stop. Okay. Okay, let's stop. I'm gonna clear the screen and then we're gonna stop and we're gonna do our last question before we end the session today. Yeah. I'm clearing the screen. Remember, if you write after this part, I can see who's writing. So you don't want to get yourself into trouble. Clear all drawings, back to a clean whiteboard. Thank you. I hope you guys got that out of your system right now. Okay. So the last question we're going to do is the question we did for winter school, right? Um, Clara says, stop it. I don't like it. Okay. So question 6 says, a police van with its siren on travels at a constant speed between two observers. So I want you to picture this, right? I suck at drawing, so just imagine what I'm drawing works. So we've got a police van. Okay, wait, let me do it. So there's this police van here with its siren lights there, blue and red. It's traveling between two observers, right? So there's going to be observer one and observer two. So observer one is there, observer two is there. Okay, at a constant speed between the two observers. A and B, not one and two. Sorry, let me quickly fix that. Not take the head off, just fix it. A and B. Observer A detects a sound with a frequency of 545. So A hears 545 hertz. Observer B detects a frequency of 615 hertz, right? State the Doppler effect in words. We're going to skip that because we've been doing it already. Then it says there, 6.2, in which direction is the police van moving? So you're going to say either towards A or towards B and give a reason. In the chat, I want you to just say towards A or towards B. So it's moving between two observers. A hears 545, B hears 615 hertz. So in the chat, write towards A or towards B. That's all I want you guys to say. I'll give you guys 30 seconds to put your answers in. 5, 4, 3, 2, 1. Let me quickly check there. Look at my answers. Look at the answers. Okay, I need to think, how am I going to celebrate this one? Let me think about how I'm going to do this one. Okay, let me quickly put my reaction before you guys put your reaction in the chat. Boom. Okay, starry eyes. You guys blow my mind every time, right? So 100% it's moving towards B. The one that hears the higher frequency has the sirens coming towards them, right? And if it's moving away, it's going to hear the lower frequency. Okay. Just a quick heads up for those of you that weren't at winter school, this question is going to be a little bit challenging, but you guys have been doing so phenomenal so far. I felt comfortable enough to give you this question again, right? And hopefully this time we're going to nail it together. For those that had seen it and those that hadn't seen it, I know you guys are going to kill this question. Okay, so the right answer is towards B. The reason for it being towards B is pretty simple. It's going to be because the frequency detected by B is higher than that detected by A. Quickly there. So the answer is going to be towards B because the frequency detected by B is higher than the one detected by A. 100%. Thank you guys for your celebrations there. If you got it right, yeah. Well, not if you got it right. You guys all got it right. So give me those celebrations. Seeing some alien eyes, some brains and hearts and stars and firecrackers. I'm seeing some really crazy celebrations there. You guys are awesome. Okay. Then it says the speed of sound in air is 343 meters per second. Calculate the frequency of the siren. Notice this question is not 3 marks, it's not 5 marks, it's 7 marks. That tells us a lot about this thing here, right? So let's start. Let's look at our information there. We got the speed of sound in air. And now we've got 2 detected frequencies. This is a bit confusing, right? What do we do with that? Let's go look at our equation at the same time. So why have they given me 2 detected frequencies? What do I do with 2 detected frequencies? Thanks, Sandika. We need a simultaneous equation, right? And another reason why you'll see we need a simultaneous equation is when you put your equation down, you'll say, you'll have the frequency of the listener is equal to V plus or minus VL divided by V plus or minus Vs times Fs. And when you try and figure out what information you got and what you need, you'll say, do I have the frequency of the listener? Well, yes, I've got that. Do I have the speed of sound in air? Yes, I've got that. Do I have the velocity of the listener? Well, yes, it's 0, right? Do I have speed of sound in air? Yes. Do I have the velocity of the source? I don't know how fast it's moving, so I don't have this. Do I have the original frequency of the source? No, I don't know what frequency of the source is. So when you put your equation together, you'll see, oopsie, I've got 2 unknowns. That's the first hint to say, ooh, if I've got 2 unknowns, I either need to go find one before I find the next, but more likely than not, the fact that you're going to be given 2 of the same type of information, because this is what was observed, this is going to be frequency of, not source, but frequency of the listener. That's also going to be frequency of the listener. If I have 2 of the same kind of information, that tells me again, another hint. This has got to be a simultaneous equation. Okay, so let's quickly do that. And when you do a simultaneous equation, what do we need? We need 2 equations. So let's do the 2 equations quickly, right? One is going to be towards, one is going to be away. So we have to write our 2 equations correctly, right? So for the away one, we know that it's going to be minus plus. For the towards, it's going to be plus and minus. So let's first do the towards and then we'll do the away. So let's say towards. So the frequency of the listener equals, so towards is going to be plus minus, right? And we know that the listener is stationary, the source is the one that's moving. So we're going to have V over V minus Vs times Fs. Then for my away, I have the frequency of the listener is equal to, that's going to be away is minus plus, right? So it's going to be V over V plus Vs times Fs. Those are my two equations I need to put together. Let's substitute our values, right? So for my first equation, or my equation 1, my towards, let's call this 1, and away, call that equation 2. So for towards, frequency of the listener, it's moving towards B. So B detected 615. Let's quickly put that down. That 615 is equal to V was given to us as 343 there. 343 divided by, oopsie, oh, sorry, 343 minus Vs times Fs, right? That's number one. And then the next one, we're going to then have in red, frequency of the listener was 545, which is what the listener A was. So that's 545 is equal to 343 divided by 343. Let me quickly fix that. 343 plus Vs times the frequency of my listener, of the source, times Fs. So I've got two equations there that I need to now solve simultaneously, right? What you can do if you'd like there is we can then solve for one, let's say the velocity, then use the velocities to solve for the frequencies. One thing that we do know that will be the same on both of them is the Vs and the Fs. What I find easier is I'm going to solve for Fs first because it'll be the easiest thing to isolate. Once I've isolated it, I'm going to then use that answer, substitute back, and solve for Vs, right? So when we do that, we can do the following. I'm going to first write out both equations, making Fs the subject of the formula. Let's do that on both equations. So for number one, making Fs the subject of the formula, we find that Fs equals 615. I'm going to multiply both sides by my denominator. So I'm multiplying both sides by this here to cancel it on the right-hand side and then add it to the left-hand side. 615 times 343 minus Vs. And then I'm going to divide both sides by 343 to then remove this on the right-hand side and then take it to the other side there. Okay, that will be divided by 343. Now I've taken equation 1 and written it with Fs as the subject of my formula. Let's do the exact same thing on the second equation. So remember, to get Fs by itself, I'm going to multiply both sides by the denominator to get rid of this denominator. I'm going to divide both sides by the numerator to get rid of that numerator there. Okay, so we know that Fs is going to be equal to 545 times 343 plus Vs. And then we said we divide both sides by the 343 to get 343, like that. Now I've got two equations, right? Where Fs is equal to this, Fs is also equal to this, which means those two things must be equal to each other. Hope that makes sense to you guys. And then I'm going to equate them and then solve for that equation there, right? So when I equate them, I'll find that 615 times 343 minus Vs over 343 is equal to 545 times 343 plus Vs divided by 343. Okay, that's what we've got there. Now I can work this until I can solve for Vs, right? So my first step that I'm going to do here, I'll multiply both sides by 343. So if I multiply this by 343 and multiply this by 343, these two will cancel, those two will cancel, which leaves me with just there. So I can actually start multiplying certain values in, right? So if I multiply those values in, so I'm going to multiply 615 in here, multiply it there, multiply this in here, and multiply that there, which should give me 615 times 343 will give me 210945, and then 615 times a negative VS will give me minus 615 VS. That's the left-hand side. Let's simplify the right-hand side. 545 times 343 will give me 186,935. 186,935, right? And then 545 times VS will give me 545 VS. Now that I've got that, I can take all my numbers to one side, all my VS's to one side, and then I can solve my equation. So my positive VS is already on the right-hand side. So all I'm going to do there is simply bring this VS there and bring that number on that side there. Okay, so which will give me 545 VS plus 615 VS. That should give me 1160 VS. And then on the left-hand side, I've got 210,945 minus 186,935. And that should give me an answer of 24,010. Like that there. Okay, and now it's a simple one. I can just divide both sides by 1,160. And then I'll get an answer in that case there. When you plug that in, you should get an answer of VS being equal to 20,698 meters per second. So that's the original velocity then of my source. Did I answer my question right? No, I didn't, because the question is asking for the frequency of the siren. All I've managed to do is find the velocity of the source, which is perfectly fine. I can now take this and substitute it back to any one of my equations I had before, right? So I can either take it and substitute it into this equation or sub it into this equation. Doesn't matter which one, both of them will give you the final answer of the frequency that was originally emitted, right? So I'm going to just choose randomly the 545, the one that was moving away, right? So let's quickly put that equation out. I'm going to just copy it and paste it. Let me duplicate this. Okay, so there I've got the equation that I'm going to substitute my VS into, and then that's going to be basically be simple, because what I'll do there is where I see VS, I'm going to now substitute that value, this 20.698, 20.698, and if you plug that into your calculator, you should get an answer, frequency of the source of 577,89 hertz. Cool. I see a lot of you guys got that answer there. Well done to you guys. One final check. I need to check this answer, right? How do I check this answer? I need to go make sure that my answer lies in between my two values, right? It can't be lower than 545. It can't be more than 615. 577 is greater than 545, and 577 is lower than 615. So I know I did the right thing. Awesome. I know I've got the right answer in this case here. I can celebrate however you wish to celebrate for getting that right answer. Okay, well done to all those answers that have come through. Please throw the biggest celebrations in the chat that you've done so far, because we are at the end of our lesson today. So quickly throw massive, massive celebrations in the chat. You guys did so phenomenally well. I really appreciate you. If you guys feel like you received 5-star service from me, I would really appreciate a 5-star Google review. Now, please post the link in the chat. Yeah, so if you feel like I gave you 5-star service, we would love a 5-star review. 5-star reviews really help us to be able to continue lessons like this for you guys, because those 5-star reviews help us attract funders. They help us be able to get people who can do this and fund these sessions for you guys. And the more free sessions we can do, the better, right? For you guys. So I really love. Someone says, for celebrating, please open the whiteboard. I'll do that just now, right? There was a question that I saw that I would like to address before. Okay, give me 2 seconds before I open the whiteboard. Once I've done that, I'll open up the whiteboard just now. I need to find that question. Someone there we go. It says, Sandika says, so why do we multiply by 343 to get rid of the denominators? 100%, I'll quickly show you. So in this case here, so Sandika, what you're referring to is this part of my sum, right? And again, thank you for the really high quality questions. You tell me exactly where you need help, and that really helps me understand where to help you. So when I've got an equation that's got fractions on either side, it's not easy to solve them directly. The first thing I have to do is get rid of my denominators by finding a lowest common denominator and multiplying through by my lowest common denominator. So what I'm doing is I multiply the right-hand side and the left-hand side by 343. Remember, what you do on the left, you must do on the right. So if I multiply left by 343, I must multiply the right-hand side by 343 to not change the balance of my equation. But multiplying by 343 means I get to cancel this because this is one term. This is one term, meaning I can just cancel denominators out by multiplying both sides. The same thing would happen is if I cross multiplied and then divided both sides by 343. It would have the very same effect. So algebra is algebra. You just need to figure out how you want to work through that problem. I'm trying my very best to see if we can get grade 11 sessions going, and those sessions will do a lot of algebra, right? So in those algebra sessions, make sure to join. I think we did do algebra sessions for maths with Tsapang or one of the maths tutors or Mulanga, I'm not sure. Go back and watch those sessions as well, where you can see how to manipulate expressions. And like I said, it's a little bit unfair because in science, guys, please don't annotate my whiteboard just yet. I will give you a chance just now, just now, just now. Um, in science, you don't get marks for doing the maths, right? The marks is for formula, substitution, answer. But the best part about that is that in a question like this, where you struggle with simultaneous equations, you literally, let me try and see if I can find the memo to tell you what you stand to lose. So out of these 7 marks, let me show you what you actually get marks for. So number one, you're going to get a mark for your main equation, right? That will give you a mark. You will get 2 marks for substitution in both of these. You'll get a mark for this and that. You'll get a mark for this and that. So before having done any maths whatsoever, you've got 5 out of 7, right? And that's the thing I keep telling you guys about how easy it is to get a 60 in a science paper. Even if you just go equation, substitution, and leave it there, and you struggle with whatever, 5 out of 7. Let me quickly calculate that. What 5 out of 7 is. 5 out of 7 is 5 divided by 7 is 71% of that question. So you really can do a lot. But what I always say is aim for the stars. Try your best, try and do stuff. The last 2 marks you get is for the answers of your substituting back into the frequency equation. Then you get a mark for that and the final answer. Okay, that's what's happening there. Before I give you the final whiteboard, there's one question left. Sorry, right? And it says 6.4, spectral lines of a certain gas observed from a distant star appear to be redshifted. Explain this observation by referring to the motion of the star and the frequency of the spectral lines, right? So in that case there, sorry, this bottom here, this thing here down here is not the answer for that question. The answer for the question, 6.4, you must talk about now redshift in terms of the motion of the star and the frequency of the spectral lines. So redshift means I'm going to have a lower frequency than I'm expecting, number one, right? Meaning this star is going to be moving away, right? So what you want to say there for this answer is the star is moving away. That's the motion of the star. So star is moving away. Away. That's making reference to the motion of the star. Making reference to the frequency is then saying the spectral lines show a decrease in frequency, right? A decrease infrequency. Perfect. That's how you answer that question. And as you guys wanted, here's your clean whiteboard. Please go crazy, go nuts. You can do your final celebration on my whiteboard. Please don't forget to go give us those reviews, guys. The 5-star reviews do a lot to help us so that we can continue to give you guys these lessons. It's been an absolute pleasure. I'll put my video back on while you guys are busy doing that. Yeah, it's been an absolute pleasure working with you guys for this session. We've got a math session tomorrow and another science session on Thursday. You'll have one of our other many really awesome tutors that you guys have been experiencing. I will be back with you guys. I think I've got a lesson. I'll double check my calendar. I think I'm teaching you guys again next week, Tuesday or Thursday.